So in today's video, we're bringing our topic about ideal gases towards a close by looking at ideal gases and the Maxwell Boltzmann distribution. Now, the Maxwell Boltzmann distribution is something that chemistry students should be familiar with from their study of rates of reaction. It is named after two very famous scientists, James Clerk Maxwell, the finest thing to come out of Scotland since iron brew, and Ludwig Boltzmann, who comes from Austria. I don't know. It was cool. It was cool. And we've seen already that ideal gases follow three useful equations. So one of the equations that we met was pressure times volume, PV, equals nRT. And little n is the number of moles, multiplied by R, the gas constant, multiplied T, the temperature in Kelvin. We also went on to see that by using Newtonian mechanics, we see that PV equals 1/3 nmc squared. So once again, PV meaning the pressure times volume. In this case, capital N is the number of particles, and m here is the mass of one particle, and c squared is the mean square speed, as in all the speeds have been squared and it's the average of the squares. Now, in a previous lesson we saw that we can put these two together because look, they're both equal to PV. We put them together and we can derive an equation, and this equation is arrogance equation because this equation says, oh, look at me, I am the most useful. But the equation is not lying. She really is the most useful equation. So here she is, 3/2 kT. So k, little k here, this is the Boltzmann constant. So it's a constant, it doesn't change. That's very useful to remember. Equals 1/2 mc bar squared. So the mass of an individual particle multiplied by the square, the mean square speed. And of course, if we look at that, oh look, 1/2 mv squared, mass times speed squared, is kinetic energy. Kinetic energy of a gas is directly proportional to its temperature. If you double the temperature of a gas in Kelvin, you double the temperature of a gas, then you double the mean kinetic energy of the particles. Well, what we're going to do today, the Maxwell Boltzmann distribution helps us understand what we mean by mean and how we can think about what other particles might be doing who are not at that mean kinetic energy. So if you have a little bit of trouble thinking about the Maxwell Boltzmann distribution, here's a story that helps you think about it. Let's imagine that we were doing a survey of all the people in the school, and in our survey we went around and we surveyed the height of the people, and we found out that there were some giant, enormous tall people, and a couple of like really short people as well. But generally, on average, a lot of people were sort of hanging around the sort of 170, 180 centimetre mark, kind of typical of young people in the UK, around 16, 17 years old. And then, because we were good students and we learnt mathematics at primary school, we might put this into a bar chart, showing the height of the students and the number of students at those different heights. And it might show a graph a little bit like this, and there's our like really short people, there's our freakishly tall people up at the top there, and there's a lot of people clumped around the middle here. Now, I am telling you this funny story about heights of people because we're going to do the same with gases and the molecules in gases and their kinetic energy. That just because this number here might be the mean height of students in the sixth form, it would be stupid to think that everybody is that height. It's just the mean height. There are plenty of shorter people, there are plenty of taller people. Gases are the same. Just because we say that this is the mean kinetic energy of the molecules of a gas, it would be silly to think that no particles had any other number for their kinetic energy. So, a bit like we just did for the heights of students in the sixth form college, we could imagine doing the same kind of survey on gas molecules, where we would measure their kinetic energy, and we would do a graph showing the abundance of molecules at each kinetic energy, producing a graph that looks not dissimilar to the histogram of the heights that we did in the last picture. Now obviously nobody actually sits there with like a stopwatch and a ruler measuring the speeds of molecules. Can you imagine? What a stupid idea. Instead, this is mathematically derived. That's why it came from two theoretical physicists, James Clerk Maxwell and Ludwig Boltzmann. So let's just notice three pretty things about this distribution. First off, no particles have no kinetic energy. That's position number one that I'd like you to note. The graph goes through 0, 0. It is forbidden for particles to have zero kinetic energy, and partially because it contradicts the Heisenberg uncertainty principle. We have a hump in the middle, so this kind of kinetic energy around that kind of value, this is where a lot of molecules are to be found. We're in and around the mean kinetic energy. The one in the 3/2 kT equals 1/2 mc bar squared equation. Meanwhile, down here you can see that as we go to higher kinetic energy, the number of molecules drops off very sharply, but we do not hit the x-axis. We merely exponentially decay away. So here at point number 3, there are still some particles with very, very high kinetic energies, even though the vast majority have maybe quite low kinetic energies. So we're going to do one cool thing with this before we try some problems based on the Maxwell Boltzmann distribution. So here's the distribution, the Maxwell Boltzmann distribution, and we're just playing a little game here about escape velocity. So you can imagine that in order to escape Earth's gravity, you would need to have a certain amount of kinetic energy to get up and out of Earth's gravity. This gives rise to a term called the escape velocity of a planet, which for Earth is about 11 kilometers per second in order to escape the gravity of the Earth. And here you can see, you can imagine if this was the amount of energy that you needed to get out of Earth to escape Earth's gravity and move out, you can imagine, well, oh, look at this. All these particles in that area, they have enough kinetic energy to escape. So light gases have escaped Earth's gravity. Things like helium and hydrogen, they escape Earth's gravity and we find very little of them in the atmosphere. Instead, we have heavier gases in our atmosphere, like nitrogen and oxygen. Well, what about a different planet? What about Jupiter? Jupiter's gravitational field strength at its surface is about 27 newtons per kilogram compared to Earth at 9.81. So it would take a lot more energy to escape from the gravity of Jupiter. And now only these molecules, much smaller proportion, would have enough kinetic energy to escape from Jupiter. So what's the atmosphere of Jupiter made of? It's made of a lot more light gases like hydrogen and helium, and not those heavy gases that we see so much more of on Earth. And there's one application of the Maxwell Boltzmann distribution.